Minor axis is the shorter one. So the shorter axis, it has a length of 2b. So I'm going to show you where b is when we graph it. So the foci are your two fixed points that you saw in the video with the pins. So those are the two fixed points. And they are located on the major axis. So whichever way your ellipse is oriented, the foci always go on the major axis, and they are located C away from the center. So you have three values that your equation is going to help you find: the A value, the B value, and the C value. And we're going to have to find our center. Center is H, comma, K, and it's the intersection of your major and minor axis. And I skipped vertices. Vertices, you have 4. They are the end points of your major and minor axis. And that's all the information that I need to give you before we try graphing one of these. And then I'll come back in a minute and I'll prove the relationship between A, B, and C. So there's a Pythagorean identity, so that if you know A and B, you can find C. Or if you know B and C, you can find A. So you only need 2 out of those 3 pieces. And then I'm going to show you in a minute the general form for whether it's a horizontal major axis or a vertical major axis. But I think it's easier to do it in action first. But on the next page, I only give you ones that we've got to convert. So let's practice completing the square. We'll take a minute and we'll actually convert one of these equations. And then I'll go back to some of the definitions after we've tried actual problem. So doesn't this look similar to the equations you just practiced with circles? Can someone see a difference right away? Does anything pop out as like, oh, that's different? Yeah. They have numbers in front of them. I have 9x squared here, and I have 4y squared here. If they were the same coefficient, you could just divide through and you probably have a circle, right? If this said 4x squared and this said 4y squared, you could divide through by 4 to get rid of the coefficients, and it's probably a circle. But because the coefficients are different, it is going to affect our shape. It's going to make it an ellipse. But the first step is the same. You're going to put your 9x squared and your 90x next to each other, your 4y squared, your minus 16y next to each other, and you're going to move the negative 205 to the other side, or you're going to subtract 205 to the other side. And you cannot complete your square yet. So because there's a coefficient in front of this x squared, I can't just cut this in half, get 45, and square it. My first step is I'm only working on this trinomial to start with. What can I divide both of these by? What's my greatest common factor? 9. So I'm only working in this kind of circled area, but I'm going to factor out a 9. So I will have x squared plus 10x plus some extra space now as part of this trinomial. So now I can complete the square inside this parenthesis. What would I add to complete the square? Cut this in half, right? 5. 5 squared is 25. So I just completed this square, but what do I need to add to the other side of the equation? Do I only need to add 25? I actually need to add 9 times 25 to the other side of the equation to keep it fully balanced, because I just added 25 inside of parentheses, right? So what is 9 times 25? 225, right? So I need to add 225 to the other side to keep this equation balanced. But this is now, I've completed my square, right? So now I'm going to go over to this other trinomial and do some work. What do I need to factor out of this part of the problem. So I'll have plus 4, and then what will I have inside my parentheses? I'll have just y squared minus 4y. So what do I need to add inside the parenthesis to complete the square? I'm going to cut this in half, -2, and then square it, +4. So I need to complete the squares inside by adding 4. What do I need to add to the other side of the equation? Yeah, the 4 gets multiplied by the 4 to give you 16. So I'm almost there. Let's rewrite this as perfect square trinomials. This would be x plus 5 squared, right? So I have 9x plus 5 squared plus 4 as my coefficient. This would be y minus 2 squared. And then I need to add -205, 225, and 16. So what do I get on the left, or the right? Okay, equals 36. Okay, I'm almost finished. I can't have coefficients in front of my parentheses. So if this was a circle, maybe you could just divide through everything by 4, but I have a 9 here and a 4 here. So you actually divide in the other direction. Whenever you have an ellipse, you need to have 1 on the right-hand side of the equation. So you actually are going to divide through the other way, and you're going to divide everything by 36 to get equal to 1 on the right side of your equation. So for an ellipse to be in standard form, it has to say equals 1 on the right-hand side. And you can change these fractions to reduce them. So 9 over 36 would be 1/4, right? So this is really x plus 5 squared over 4 plus 4 over 36 reduces to 1/9. So y minus 2 squared over 9 equals 1. I should have just given you an example starting at this step, but that's okay. We practiced the algebra to get there. This is what I want to break apart for you is when you're in this form, how do you graph an ellipse? Because this is what I want to define on the front page. So guess what? You find your center the same way that you find the center of a circle. So my center is left 5 and up 2, and so I still mark my center. So left 1, 2, 3, 4, 5, up 2. And if this had been a circle, we could just plot our radius and be done. It's not a circle, and it has this is going to be your b squared value, and this is going to be your a squared value. So kind of like radius squared is in your equation, your a squared and your b squared values are in your equation. And what did we say that a was? A is the major axis, 2a is the major axis. So a is currently positioned under the y. So that tells you that this ellipse is going to be oriented vertically in this direction, so more longer in this direction. A is going to be 3, right? Because the square root of 9 is 3. So a in this equation is 3, b in this equation is 2. And that's how far you go to plot your vertices. So from my center, I'm going to go up 1, 2, 3 units, plot a vertex, go down 1, 2, 3 units, plot a vertex. In the b direction, which is under the x, I'm going to go 2 units, plot a vertex, go 2 units, and plot a vertex, and that is my ellipse. It still looks pretty circular, but it's longer in the y direction. So you can see that this has a length of 2a, and this minor axis has a length of 2b. So there's one thing that I haven't plotted on my ellipse, and that's the foci. So your last step is going to be to figure out what c is in this equation and plot your foci on your major axis. But to do that, we have to go back to the front page, and I'm going to prove to you how to find c. So the relationship between A, B, and C. I want you to draw in a major axis and a minor axis. So this is A, this is B, And this distance right here is considered C. So this is my focus. All right, if I pulled my string, right, my string has to touch every point, right, everywhere on the ellipse. All right, so as an aside, I'm not going to draw it on this set of notes. You don't have to draw this. If I wanted to stretch out my string to reach this point over here, right, because that's a point that's on my ellipse, how long would that string actually be? So I have one string that's coming all the way from this focus, and I have another string that's coming from this focus, right? Imagine that this is my string. I'm pulling it tight, so it's literally, it's mashed onto this, it's right on that x-axis, but I'm pulling the string tight to get to this point. How much does this little piece of string plus this little piece of string add up to? Well, isn't this distance equal to this distance, right? Focus to vertex must equal focus to vertex. So couldn't I just cut this piece of string and put it right here? So how long is my string? My string is actually 2a in length, right? Because if I wanted to reach every point on the circle, I have to reach this point too. This is the furthest piece on the whole circle, or on the ellipse. And if the string is stretched tight from the two focal points, this piece of string has to fit in this window if this is equal distance, right? So this length is 2a. So if the string is equal to 2a, and I want to reach up to this point, right, from my two focal points, right? Here's my string again, right? The string always equals 2a. If you want to reach this focal point, don't you have an equilateral triangle right now? So this has to be A, this has to be A, and the height was B. So you have a Pythagorean identity between A, B, and C. C is this distance from the center to the focus. B is this distance on the minor axis. And if we just said our string has to be 2A, if this is an isosceles triangle, then A has to go here on both of those strings to make them equal. So do you see the Pythagorean identity? A squared has to equal B squared plus C squared. C in this case is not the hypotenuse, right? A is this length on the major axis, so we're calling this A. A squared equals B squared plus C squared. That might be tough for you to remember, but A is always going to be the biggest value. The hypotenuse is always the biggest value. So we're going to use this Pythagorean identity to mark our foci onto our graph on the next page. And this is a lot of information to take in. So you got to do this, 5 or 10 times until an ellipse becomes, second nature. So we've only done it once. This is like, painstakingly a lot of information. I know what A and B are. I need to find C to plot it on my axis. So A squared equals B squared plus C squared. I need to solve for C in this Pythagorean identity. I know that A squared is 9, and I know that B squared is 4. So what does that make C squared? If 9 has to equal 4 plus C squared has to be how much? 5. Subtract 4 from both sides. C squared is 5. So what does C have to be? The square root of 5 is 2.2. Is that what you said it was? All right, so I'm going to walk from the center 2.2 units, and there's my focal point. Right? So just kind of dot them, but I'm going to be looking on your, work that you actually did calculate the C value, so you know that that is 2.2 units away from the center on the major axis. It's kind of like adding an asymptote to the graph. You add your focal points to the graph. All right, let's go back to this page and add our standard conics form for an ellipse whose center is at H, K. The vertical major axis is when the ellipse goes in this direction. The horizontal major axis is when it goes in this direction. So if it's horizontal, where does the a squared value have to go? Does it go under x or does it go under y? Under x. So you'll have x minus h squared plus y minus k squared equals 1. This would have almost been a circle, right? X squared plus y squared equals r squared. We put a 1 on this side, and then your a squared value and your b squared value go underneath your fraction. So this tells me the major axis is in the x direction. So the only thing that changes between the two equations, you still have x minus h squared, y minus k squared equals 1. Just a squared and b squared switch where they're located. So if it's going in the vertical direction, the bigger number is going to be under the y value, just like we did in that example. And it says, notice, both forms have to be set equal to 1. So you're not allowed to read your equation until they are set equal to 1. So this is a formula that you're just going to get used to seeing. You're never going to have to write this out with all these variables, but if I give you an equation, let's just, let's just skip example 2 for now and just use this axis to do a practice question. So if I gave you x minus 4 squared plus y plus 1 squared equals 1, and I told you that this was 25 and this was 16. Let's see if we can figure out how to graph this when it's in ellipse standard form. So I just made this one up. We have plenty of these to practice tomorrow. If you look at like the back page here, there's a bunch of them to practice. So, all right, so I find my center first. My center is at right 4, comma, negative 1. So 1, 2, 3, 4, negative 1. There's my center of my ellipse. And again, I ended up putting the bigger value under y. So this is a squared and this is b squared in this problem. So a by itself is just 5 and b by itself is just 4. So using those two values, you can now dot in where your 4 vertices are going to be. So in the y direction, vertical, you're going to go up and down 5 units from your center. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So those are the endpoints of your major axis. Then in the x direction, because b is underneath the x, you're going to go 4 units from the center. 1, 2, 3, 4. 1, 2, 3, 4. And that's all you need to graph an ellipse is your 4 vertices. And then just connect them the best you can. Try not to draw like a diamond, but you know, it should look kind of elliptical, so kind of curved. Don't just connect them with straight lines. And then your last step is to use the Pythagorean identity to plot where your foci are located. And I always write out the equation for myself, and then I can fill in the pieces of information that I already have and solve for the c value. So I know that a squared in this equation is 25. And I know that b squared in this equation is 16, and it's my job to solve for c. So subtract 16 to the other side would give you 9. And then take the square root to get c by itself. So c is 3 units away from your center on the major axis. So in the vertical direction, you're going to walk 1, 2, 3 units from the center and plot your foci. So you've got your 4 vertices, your center, and your 2 foci for your ellipse. So maybe tomorrow we'll be able to work through some more of these examples with the ellipse.